Hello, everyone. My name is Shali Jian. Today I'm going to talk about efficient, non-myopic batch active search. This is a joint work with Gustavo, Matt, Ben, and Roman. Many real problems involve searching for valuable items from a large pool of candidates in an iterative fashion. Drug and materials discovery are two typical examples. We formulate this problem as active search. Suppose there is a big pool of unlabeled points. A few of them are positive, and most of them are negative, and you want to identify the positives. Now suppose you have an inference model that gives you the probability of each point being positive. Now given this information, you can select the points and query an oracle. Is it positive? Then oracle will answer your query with a certain cost. Now based on this new observation, you can update your model and repeat this process. Your goal is to identify as many positives as possible in a given number of queries. The key question we study here is how to select a point. Our previous work studied the case of selecting one point at a time. However, in many real applications, we can often query multiple points in parallel. So in this work, we study how to select a batch of points. The most straightforward policy one might think of is greedy. That is, always choose the points with highest probabilities. This is optimal in terms of maximizing the expected number of positives in this batch, and it's computationally efficient. However, it's myopic, ignoring what could happen in the future. How can we do better? So we propose non-myopic batch policies. That is, we consider not only how much we get from this batch, but also the expected future reward if we choose this batch now. However, this policy is computationally intractable, since we have to recursively simulate a search tree of size exponential in the remaining budget. We adapt an idea developed in our previous work and compute an approximate expectation by assuming conditional independence after this batch. This is efficient in sequential setting. However, in batch setting, it becomes combinatorial search. We propose two approaches to tackle this challenge: greedy maximization and sequential simulation. Greedy maximization is a common practice for maximizing set function. We'll briefly talk about the second one, sequential simulation. The idea is simple. We simply simulate a sequential policy by selecting points one by one to add in the batch. And we use fictional oracle to fake the label and update the model based on the fake label and selecting the next one. The key question here is, how do we assume the label? For example, you can sample a label. You can use a most likely label or always assume positive or negative. Interestingly, we find always assuming negative performs the best. And this is because assuming negative creates repulsion. And this repulsion encourages diversity of this batch and hence better exploration of the search space. We find that our non-myopic policy improves over myopic ones by a large margin and demonstrates nice exploration-exploitation behavior. Batching is certainly more efficient, but is that something we are compromising? Suppose we can query 20 points. We can either query points one by one for 20 iterations, or say we can query 5 points at a time for 4 iterations, which is much more efficient. However, in the latter case, the points are often chosen in a less adaptive fashion, which could lead to worse performance. But how much worse? We prove that the performance ratio between optimal sequential and batch policies is at least linear in batch size. And this theoretical result is found to match our empirical results. And this insight could help us choose the batch size in cases where we have many options. Thank you for your attention, and welcome to stop by our poster 131 in level 5. Thank you.